Hello, my name is Carson Stewart, and this presentation will focus on a titanium alloy material, specifically titanium 6 aluminum 4 vanadium, and its fabrication of parts by selective laser melting and electron beam melting. The title of the research paper I will be referencing is the comparison of the microstructures and mechanical properties of the titanium alloy fabricated by selective laser melting and electron beam melting. This paper can be found in the Materials and Design Journal, volume 95, pages 21 through 31. The specific scope of this study is the comparison of the microstructures, defects, and mechanical properties of the titanium alloy samples fabricated by SLM and EBM methods. The key question is, what effects does part size and printing orientation have on the defects, microstructure, and tensile fatigue properties of the titanium alloy samples fabricated by SLM and EBM methods? The picture to the right shows the 6 samples that were produced differing in size and printing orientation. Again, the material used in this research was medical-grade titanium 6 aluminum 4 vanadium powder. The titanium alloy samples were produced using an RCAM A1 EBM machine and a Realizer SLM 100. For the EBM, a voltage of 60 kilovolts and electron beam size of 200 micrometers was utilized. Helium was used as the regulating gas, and an energy density input of 76 joules per cubic millimeter was calculated. The EBM process was operated with a speed function of 39, scan spacing of 0.2 millimeters, and a layer thickness of 0.05 millimeters. The illustration on the right shows the operating procedure of a standard EBM printer, where an extruder lays down a layer of titanium powder, in this case, an electron beam selectively melts the powder in a vacuum chamber. The process is repeated until a part is built layer by layer. For the SLM printer, a laser spot size of 40 micrometers and a laser power of 200 watts was used. Calculated input energy density was 40 joules per millimeter cubed. The SLM was operated with a scan speed of 1000 millimeters per second, a scan spacing of 0.1 millimeters, and a layer thickness of 0.05 millimeters. The illustration on the right shows the operating procedure of a standard SLM printer, where a layer of powder is swept across the build plate and a laser selectively melts the powder. This process is repeated until a part is built layer by layer. The printed parts were characterized by their microstructures, defects, and mechanical properties. The microstructures were analyzed by optical microscopy, a scanning electron microscope, and a transmission electron microscopy. The defects of the parts were analyzed by micro CT images that were then reconstructed using Exum Reconstructor software. The mechanical properties were tested on an Instron 8872 fatigue testing machine at a strain rate of 1.3 times 10 to the negative 4 per second. The fatigue tests were performed at a stress ratios of R of 0.1, a frequency of 30 Hz, and a sinusoidal cyclic waveform loading. Key results for defect effects. The illustration on the right shows the combined results from the CT scan and pore distribution for samples in vertical orientation of different part size. As shown in the CT scans, pores were the main defects in the printed parts. Also shown in the CT scans in the top right corner, pores were in EBM samples were almost spherical, where in SLM they tend to be irregular in shape. No significant variation in porosity was found for differing part size, but porosity in SLM samples were much higher than the porosity in EBM samples. Also, not shown in the graph, but another observation was that the horizontal orientation had a greater number of pores than the vertical orientation. Key results for mechanical properties. The graph on the right shows the ultimate tensile strength, yield strength, and elongation measured for the various samples printed on SLM and EBM. As shown in the graph, the strength of the SLM samples measured higher than those of EBM samples, whereas the ductility is much lower. For EBM, the strength increases with decreasing part size. However, for SLM sample, strength decreased with part size. For both EBM and SLM, the strength and ductility along vertical orientation is slightly higher than along the horizontal orientation. The illustration on the right shows the stress versus number of cycles to failure data for the samples fabricated by EBM and SLM processes and the vertical orientation. Key takeaways from the data was that EBM have a slightly higher fatigue limit than the SLM parts, with EBM parts being shown in the black and red and SLM in purple and blue. It was also determined that pores were the dominant feature that controlled fatigue performance. This can be observed in the graph, as samples shown in red and blue that had pores sealed by heat treatment greatly outperformed those that were as fabricated samples. Key results for microstructure defects. The graphic shown shows the optical microstructures of EBM and SLM samples with different part sizes along vertical orientation. As shown in the graphic, the EBM samples were composed mostly of alpha lamellas, where the SLM samples contain much thinner and longer martensitic lathes. Thickness of the lamellas in the EBM samples decreased with size, which explains the increase in strength properties with the decreasing part size. The thickness of the lathes in the SLM samples did not vary with size. Not shown in the graph, but observed in the study, was that both SLM and EBM samples in both the vertical and horizontal orientation were dominated by columnar grains which tended to elongate along the building direction. There were three key conclusions from this research paper. For the first one, it was EBM and SLM titanium alloy samples in the vertical orientation possessed higher ultimate tensile strength, yield strength, and better ductility than those in the horizontal orientation. The second conclusion was that poor defects were present in both EBM and SLM samples, but compared to EBM samples, the porosity of SLM samples were much higher. And the third conclusion was that the thickness of the alpha lamellas decreased with the decrease in part size during EBM fabrication as a result of the faster cooling rate. This resulted in an improvement in strength and decrease in ductility. For SLM samples, the part size had almost no effect on the mechanical properties. In summary, I found this research to be very useful when comparing the printing capabilities of SLM and EBM for the fabrication of metallic parts. I find that the data collected from this study indicate that the endless possibilities that A&M methods possess for the future of manufacturing.